dark matter. Kathryn, please take us forward.
All right, so good morning on this beautiful rainy Saturday morning. It's part 2 of 3, marching down dark matter, the subject of dark matter. And so I've decided to spend the better part of today's discussion on the classic dark matter candidate. So what I want to do is to just pick out the few features of supersymmetry that pretty much dominate all of the experimental signatures and set the natural scale for which you go and look for supersymmetry in direct and indirect negation experiments. Okay, so basically what I want you to walk away from this 1 hour talk is just, basically something that you can count on your hand when you listen to talks of what are the gross features of supersymmetry that we're going after in our okay, and then basically this afternoon we'll be focusing on looking beyond the vanilla wind and what kinds of features you want to build into your detection. Okay, so standard SUSY dark matter. So we know that supersymmetry by now, 35 years into it, is pretty much the classic. It's the thing that we kind of use as our benchmark to judge all other dark matter candidates, I would say. And this is not completely without reason. It has all the ingredients, and they're present there in the theory for other reasons. So that's something to say for this setup. Dark matter sort of comes for free. So the usual picture of dark matter is that it's a single stable, weakly or sub-weakly interacting particle that's neutral. And within supersymmetry, you get all of these features pretty much for free. So let me just start with the very basics. So to make a candidate absolutely stable, you need some type of asymmetry. So in the standard model, you actually have 3 of these symmetries. The proton, which is stable by baryon number, a global symmetry. The electron, which is stable by electric charge. And the neutrinos, which are stable by, again, another global symmetry, lepton number. And SUSY has a built-in symmetry that stabilizes the lightest of the superpartners. So what you do is you take the standard model and you double it. So by now this is not controversial, at least from a theoretical point of view. And one of these states ends up being stable by R parity. So R parity, I would say, appears in many UV completions. And this was actually put in not to stabilize the dark matter, but to solve a different problem. And that was within supersymmetry, the fact that you tend to induce proton decay. And the basic reason for that is as soon as you introduce scalar superpartners, for all the standard model fermions, you induce additional interactions. So if I just take so these are actually the same operators that we saw yesterday in the context of asymmetric dark matter. So if I just say my theory needs to respect the gauge symmetries of the model, and now I have scalar and all these additional scalars floating around, that actually allows me to write down all of these additional operators that weren't there in the standard model. And the reason why they weren't there is because if all of these fields were fermionic, then I violate Lorentz invariance. It's a bad thing. But now that I have a scalar, a partner to play with, I can write down these 3 these additional interactions where I have a fermion talking with 2 fermions talking with the scalar. And if you just write down the kinds of interactions now, processes that are induced by these additional terms, they pretty rapidly cause the proton via these scalar superpartners to decay down to, say, a positron and a pion. You have to make these coefficients very small in order to prevent those kinds of processes. And that tends to be, and that is a natural, because even if these coefficients were small at some scale, just ordinary renormalization group running would tend to generate them at loop order. So this is a natural. So what people do is what they always do when something looks unnaturally small, is to introduce a new symmetry to forbid those kinds of interactions. And that symmetry that people introduced was called R parity. And R parity is just defined by putting in a combination of baryon and lepton number and then a spin of the particle. And so by construction, all the standard model particles carry R parity of +1, and you can just go through and check that. And all the superpartners carry R parity of -1. Okay, and so as a result, if R parity is symmetry that's conserved by the theory, the lightest particle that carries R parity -1 is going to be stable. Okay, and that was just the consequence of putting in this symmetry in order to make the proton stable. So that's the first one. So you have a stable particle. The lightest stable particle just comes out for free. We now, the second ingredient is dark matter should be pretty close to neutral. And you've got a few possibilities. So we know in the standard model that if you want to take the, I would say the electroweak eigenstates and turn them into the mass eigenstates, there's some mixing matrix that describes that. So there's superpartners, the gauginos also mix. And there's going to be neutral and charged states that are associated with the superpartners of these states, and you diagonalize the mass matrix to obtain the mass eigenstates. So for the neutral states in supersymmetry, in the minimal supersymmetric standard model, this is what the mass matrix looks like. So you have the superpartners of the B and the W gauge bosons, and then you have two partners of the Higgs boson. Now in supersymmetry, unlike in the standard model, you need two of these states. And the basic reason for that is in supersymmetry, it's holomorphic. Okay. The structure of the theory demands that I can't write down terms that involve both the field and its complex conjugate. Okay, so in the standard model, the reason why I only need one Higgs field, and you can do this exercise, is that I can write down a coupling of the Higgs to the up-type quarks, and then the symmetries of the theory demand that it has to be its complex conjugate, carrying opposite hypercharge, that couples to the down-type into the leptons. And that's perfectly fine because I can write down interactions that are non-holomorphic. In supersymmetry, it turns out, for technical reasons, that I can't write down an interaction that looks like that, and so therefore I need two separate fields to couple the up and the down type quarks, and by extension to the leptons. Okay, so that's why I end up with an extension that's about 2. And this parameter tan beta relates the size of the BEFs of the up type and the down type. Now the gauge couplings don't care about this flavor. And so the total BEV is just the square of the two. Okay, so that's why you have this additional free parameter that shows up in supersymmetry. So then besides that, you can see that the structure of the Higgsino sector depends on the Z boson mass, the Weinberg angle, so both of these are fixed. And then I have this tan beta parameter, and that's free. I have a mass that mixes the up and the down type Higgsinos. So this is just a term which is mu H2HD. I didn't write it down here. But because these two carry opposite hypercharge, I have to write them together as a pair. That's how the mass term of the Higgsino enters. And then I have a mass term for the Bino and the Wino. Okay, so I have 4 free parameters: tangent beta, mu, M1, and M2. And all the properties of dark matter are set by those 4 parameters. Okay, and so what we're going to basically be doing is asking, how, when I take various limits of those parameters, what is it that my observational signatures are? So in addition to those 4 neutral states, The other option is the superpartner of the neutrino, this neutrino. And this is highly constrained, at least in the minimal supersymmetric standard model, because the interaction with the Z boson is what dominates the phenomenology. So in particular, the scattering of this scalar state by the Z boson is what dominates the direct detection rate. So I want to spend some time talking about the scattering of this neutrino. This diagram says neutralino, but you can swap in this neutrino via the Z boson off of nuclei. Okay. So in general, there are two types of interactions that people commonly look at. That's not actually true, really more generally, and we'll talk about that in just a little bit. But people talk about spin-independent and spin-dependent interactions. The spin-independent couples with the total charge of the nucleus. So it's just the fact that when the momentum transfer is longer than the size of my nucleus, I see the entire nucleus all at once, and so I get an enhancement in the rate that goes like z squared. Z or A, which is the charge and the mass number of the nucleus. So in the case of the spin-independent interaction, the Higgs is the one that we normally think of. And I'm sure all of you have seen this plot many times. Okay. It's now actually a few years old, so there's an update of this. But what it shows on it is dark matter mass, which you'll note cuts off at 10 GeV. I want to explain to you the kinematics of why that's true. And it has this behavior at large mass, where the sensitivity to the cross-section just scales inversely with the mass of the dark matter. And the reason for that behavior, which we'll also see, is simply that the number density of the dark matter is dropping like 1 on m, because the energy density is fixed. And so there's really no kinematics that's changing up here at higher masses. It's really that simple. It just scales like 1 on the mass. And then what you'll see is this orange blob. Okay? And this orange blob is meant to be representative of neutralino scattering off of the Higgs boson. So we want to talk about those three different features of this plot.
Does it?
Yeah.
Does it break down like the components in high wing masses?
So it's really true that the kinematics just goes like the reduced mass squared times the reduced mass times the relative velocity squared. So this type of scaling goes to very, very high masses. So eventually the cross-sections will get so big that these underground detectors won't be able to see the candidates anymore because the rock overburden will shield. Okay, but that's quite literally the point at which this starts to break down. Okay, so you can even show that for those compact objects, the nuggets that I showed yesterday. Even for that, they will have, in a certain regime, scaling that looks like this. So this continues to actually very high masses. And in fact, as I said, what you start running into is the fact that you see the rock overburden at large, very large cross-sections. So this is the kinematics of the direct detection experiments. The idea of direct detection is really classical billiard ball scattering. You give this to this is like almost the first thing that you learn. Non-relativistic billiard ball scattering. Dark matter comes in, it sees a nucleus that's initially at rest, and then it transfers some momentum to it, given this additional state. Okay, so dark matter comes in, it has some non-relativistic energy plus its mass, and then it transfers some final amount of it. That energy and momentum are conserved, and quite literally you just plug that in, go through this exercise. You can give it to your students, young students, almost high school students, maybe younger, and what you find out is that the momentum transfer just goes like the target nucleus mass times the recoil energy. And so as a result, if you plug in the fact that dark matter in our galaxy moves at 300 kilometers per second on average, with a Maxwell-Boltzmann distribution approximately, that the energy scale that you probe is on the order of tens to 100 keV, which of course is also dependent on whatever the mass of the target is. So a lighter mass target will be sensitive to smaller energy depositions. This is one of the motivations for looking at smaller mass targets like helium instead of really massive heavy ones like xenon. So apply this kinematics to scattering through the Z boson. So the interaction cross-section, we said if it's spin independent, which it will be if it's a gamma mu interaction through the Z boson, those like the charge and the mass number of the nucleus. Well, this is not what's usually plotted because this is obviously dependent on what your target is. So what people normally do is to define this conventional quantity, sigma p, which depends on the ratio of these reduced. So you divide out by the thing that's dependent on the target, and then you fix Fp and Fn. And that's this quantity, sigma p, is typically what is plotted, typically taking Fn equals 0. So then the additional ingredient that you need to get a differential rate per energy deposition just, again, goes like n sigma v. Okay, so you have it here, you have a differential cross-section, and then here's the velocity that you're weighting by integrating over the Maxwell-Boltzmann distribution, and then multiplying by the number density of dark matter. Very straightforward, conceptually. And let's just get it back of the envelope then, where we say now you would expect for this type of interaction, one slide back still, this type of interaction cross-section via the Z boson off of the nucleon, spin-independent interaction, you would just expect that the cross-section would go like the weak coupling constant to the 4th power, the reduced mass with the nucleon, and then a 1 on mz to the 4th. So just plug in those numbers, and you'll see that what comes out is about 10 to the minus 39 centimeters squared. And then you go over to this handy plot, which summarizes where we currently are in direct detection. And these are even better now, because this plot is about 5 years old. But we're sitting down here at the 10 to the minus 46 centimeters squared. That's the most recent xenon results. And so you can see that these are now ruled out, typical cross-section, dark matter mass, by about 7 orders of magnitude. So weak interaction cross-sections in these direct detection experiments are huge, ginormous, okay? So what we're probing here are typical cross-sections that are much weaker than weak. That's how good these experiments have now become. So this is why active neutrino dark matter is excluded by many orders of magnitude. And so when people talk about neutrino dark matter, they don't mean the superpartner of the standard model neutrino. It's something that's been mixed with some other field to reduce the overall interaction rate and make it consistent with these metals. So what about the neutralino? Why does this argument, this discussion not apply to the neutralino? Why does it not just have a large scattering cross-section via the Z boson and be ruled out by many orders of magnitude? And there are several reasons for that. So first of all, the Majorana neutrino is a two-component fermion, and you can check, this is another nice exercise to do, that the spin-independent interaction of the neutralino, which is this operator, it's a chi bar gamma mu chi, q bar gamma mu q, you can just check by fruitzing it that this is identically 0. So the interactions that are non-zero are the spin-dependent one, where I stick in a gamma mu gamma 5 on this side, okay, and have it talk with the gamma mu gamma 5 on the dark matter side. This is actually like an anapole interaction. This one is non-zero, but it's spin-dependent, and then there's a velocity-dependent one, which is spin-independent on the target side, but also has this anapole-type interaction on the dark matter side. Okay, so you might say, okay, this operator is v squared suppressed. We know the velocity is about 10 to the minus 3 times c, so this should be down by 6 orders of magnitude, so why wouldn't that be detectable? Or, for example, spin-dependent now doesn't get the z squared or a squared enhancement, so maybe it's down by 10 to the 4, but why wouldn't these be detectable? Well, it's actually a little bit worse than that. And the easiest way to see this, we'll come back to this in a little bit more detail, is because pure states don't scatter by the Z boson at tree level. Okay, so the bino and the lino, they're electroweak singlets. They don't couple to the bino and the lino. Well, the bino is an electroweak singlet. The lino is not an electroweak singlet, but it does not couple to the Z. The hexeno does couple to the Z, but in the limit that the bino and the lino decouple, we can go back and see this in this mixing matrix that I wrote down. So if the bino and the lino decouple, that means I take M1 and M2 to be large. And so therefore, the only part of this matrix that we're left with is this small 2x2 submatrix. And you can see that in that limit, the neutralino is necessarily equal part up and down type hexeno. And so then you can write down, using the supersymmetric rules, what the coupling is to the Z boson. And it has this pesky little minus sign. Okay, and that implies that in the limit that I have a pure hexeno, it also does not scatter via the spin-dependent interaction. Okay, doesn't couple either to the Z boson. So what that leaves you with is that neutralino scattering off of the nucleus is necessarily Higgs-mediated scattering, at least at tree level. So we'll talk in a little bit about one-loop processes, but at least at tree level, scattering is dominated by Higgs exchange. So you can calculate the contributions from scattering off of the quarks. What actually dominates the interaction of the neutralino with the nucleus is a one-loop process where you couple to the gluons in the nucleus, and you can calculate the size of the effective coupling via this anomaly graph. That was done in this nice paper, which I recommend that you read. And so now you again have all the ingredients that you need. So it depends on, you might imagine, the up versus the down type beds, because that is what fixes this effective coupling to the quarks. You can see that it enters even here in the gluon coupling term, that it depends on the effective coupling to the quarks. So it depends very strongly on tangent beta. And it's in addition to the total Bev. Okay, so what you end up getting by doing this calculation is that the cross section depends on, for example, the downward hexeno component, this tangent beta factor, and the mass of the Higgs boson. But you can see that it ends up closer to this 10 to the minus 45, 10 to the minus 46 centimeters squared cross section. Okay, so this is what we're going after in this orange blob here. So you can ask, well, if I keep drilling down in the direct detection plane, going through this orange sweet spot where you expect to see dark matter scattering by the Higgs boson, let's suppose I get all the way down to the neutrino background, I don't see anything, and let's say I even get a little bit lower. Have I ruled out neutrino dark matter? And the answer to that question is no. Okay? Because even the couplings to the Higgs boson I can actually turn off. Okay? And that's coming back to this fact that, at least within the minimal supersymmetric standard model, the fact that the couplings to the standard model are related to the supersymmetry couplings, that fixes the interactions that can occur. So there's this other pesky fact. So we said that if I decouple, so the wino and the bino don't couple to the Z at tree level, and if I decouple the bino and the wino, the hexeno also doesn't couple to the Z at tree level. Similarly, it's also true that the Higgs does not interact with the pure neutralino at tree level. So if I have a pure bino, or hexeno, the Higgs does not couple to that state, and you can see that again through the supersymmetric interactions. So here's the up and the down type Higgs, here's a neutralino. So you can see that if this is my mediator, the Higgs, here, what it does is it takes a wino and it turns it into a hexeno, either an up or a down type one. Okay? And similarly, the Higgs will talk to a bino and turn that also into an up or down type hexeno. So there's quite literally no interaction that I can write down at tree level that will allow the Higgs to just talk to a Vino coming in and out of the process, or a Vino coming in and, all the neutralinos. It just doesn't couple because there's no interaction that will allow that. So you have to have a certain amount of mixing, and so the rate always depends on the size of that mixing. Okay, so in addition to direct detection, there's also indirect detection. So you have annihilation processes where the dark matter goes through parafermions via a fermion, a Z, or a Higgs. Or it can annihilate to the gauge bosons. Now the thing that's nice about this process, so first of all, is that this is irreducible, and they typically dominate if the dark matter is largely Vino or largely Higgsino. And it's also pretty independent of the spectrum of the other states. So for example, this diagram is going to depend on how heavy my other superpartners, my fermionic superpartners are. But really all these depend on is the gauge interactions in the standard model. So once I have supersymmetry, I have the standard model, I just get this. It's just there. It's fixed. And the size of the annihilation, I don't have any wiggle room. It just tells me what the mass of the dark matter should be and what its annihilation rate is. So let's focus on those bottom processes. So indirect detection. So if I annihilate to gauge bosons, they decay, and they can either kick off radiation in the final state. You can produce photons directly via decay of pions, for example, or charged particles can upscatter off of other photons in the galaxy. And so there can be strong indirect detection limits. And I said that it was highly predictive if I had pure Vino or Higgsino dark matter. So let's take a look at the limits. So if I look at the annihilation cross-section of dark matter to photons, as a function of the mass of the dark matter, you can see that the constraint on this annihilation cross-section, if it just goes directly to photons, is actually quite large. It's quite strong. Okay, so the thermal annihilation cross-section is up here at 3 times 10 to the minus 26. Okay, it has some dependence on the mass, but you can see that that's well above these cross-sections that are being constrained. However, this is for direct annihilation to photons. So if instead I have an annihilation to gauge bosons, I'm going to produce many lower energy photons. Okay? And so in general, the constraints on processes that don't produce a line are much weaker. So instead you can go and look at what happens when, as a prediction for dark matter to, so in this case, this is pure Vino dark matter. So this is the annihilation to gamma-gamma, or gamma-Z, as a function of the dark matter mass. The natural mass range, where Vino or Higgsino dark matter will produce the observed relative abundance, is right around 2 to 3 TeV. So you should pick up this mass range right here. And this is the predicted annihilation cross-section. What they did in this paper was to compute corrections to this process, to the leading tree level process. Okay, so they computed one-loop corrections. So you should take a look at the red line as being the best approximation. And now let's pick out this region here. And this is the current constraint from Hess. And you can see that there's actually quite a bit of tension because of these enhancements here are Sommerfeld resonances. You can see that it's actually enhanced, and it's actually pretty strongly constrained already in this few TeV mass window. Okay. Now you might say, well, there's some model dependence here because it's a constraint that's derived from looking towards the galactic center. But you can see nonetheless that there is actually quite a bit of tension already with Vino dark matter being consistent with these indirect detection constraints. Okay. I think I already said this, but just because of the fact that you can calculate these indirect detection cross-sections, but this 3 times 10 to the minus 26 centimeter cubed per second is the natural mass scale is 1 on 2 TeV squared. So thermal Vino or Higgsino dark matter is heavy. So all of these constraints, pure Beano dark matter escapes. Okay, so while Beano and Higgs-Eno neutrino dark matter may be constrained by indirect detection, Beano dark matter doesn't have this process, and it completely escapes. And the Beano, as we said before, also does not couple to the Higgs at tree level. So the indirect detection constraints also do not apply to the Beano. So it seems like even if you drill down all the way through that Higgs interacting window, and even if you see something in indirect detection, it seems like the Beano will still escape. But even the Beano is going to have a Higgs-Eno component. So if we come back here to our mass mixing matrix, in order to make the dark matter pure Beano, which is set by this mass scale M1, I effectively need to push up both N2 and this mu parameter. And the reason why that is significant is because the mu parameter also enters into the properties of electroweak symmetry breaking. So that's what's written here. You can show that the Z boson mass depends on the soft breaking parameters, the down type and the up type Higgs masses, and also on the mu parameter. So now none of these things are physical. Okay, so I'm free to dial them in order to reproduce the physical thing, which is the Z boson mass. And I said that we need to push mu up way above the Beano mass in order to make dark matter pure Beano. But you see immediately that if I do that, I pay a price. And the price is that the Z boson mass sits right around 100 GeV. So if I push this way up, well above the weak scale, I pay a fine-tuning price. And the more pure that I have to make the Beano in order to evade all of these constraints, which is to say the more I drill down to smaller and smaller direct detection cross-sections, the more I pay this price. So what's going to happen is that you're always going to be able to tune the theory further and further in order to evade the direct and indirect detection constraints, but it's going to come at the cost of additional tuning in the theory. Not unlike the story of what's going on with the OC right now. So how much parameter space escapes? And of course, whenever you project something onto a plot with some axes, it's never a precise, very precise notion of how much parameter space is being covered. Nevertheless, okay, it does give you some idea that if I look in the tangent beta versus mu parameter space, and then I look at what can be covered, for example, by xenon 1 ton, what happens is that all of this parameter space, this is an old plot now. Okay, this is basically what's already been rolled out by the recently released results of xenon 1 ton. Is that all this parameter space gets colored, and what you are left with is a region of parameter space where I've taken a particular combination of couplings such that the interaction with the Higgs boson is very close to zero. That's exactly what that one is. Okay, so you should think of it as you're going down to smaller direct detection cross-sections, you're pushing yourself into a smaller and smaller window of parameter space very close to where I've chosen the parameters of my theory such that the tree-level coupling to the Higgs boson vanishes. Okay, so the natural thing to start asking is when should we start looking elsewhere? Okay, so the takeaway that I want you to get is that indirect detection is a natural place to look for Beano and Higgs-Eno dark matter. Beano dark matter is already being constrained by indirect detection, although it's dependent on the profile towards the galactic center. Beano dark matter is very hard to probe, but you have to tune the parameters of the theory to make the dark matter pure Beano. So there's a question that the community has to ask itself as we drill down closer and closer to the neutrino background is when do we start looking elsewhere? Okay. We're not going to be able to kill the scenario, but it does become increasingly tuned. And I think for many people, also just because of the sheer challenge of these experiments, the answer is at the point at which we start really probing and seeing the neutrino background. Okay. time is it, by the way?
You have half an hour.
I have half an hour more. Okay.
Let's say 25 minutes.
25 minutes. Okay. So then I'll keep moving. Is that there are well-motivated candidates that are much less costly to probe. Okay. So what do we mean by massive dark matter? So when we look at the formation of structure, someone asked me yesterday after or maybe it was during the lecture, about why not just make neutrinos dark matter. And the basic reason is that neutrinos don't pump. They're very light. They move quite quickly, and so if you try to put them into a gravitational potential well, they want to run out of it. Okay? They erase structure. So the way you state this technically is you look at the power spectrum as a function of the scale, and this is the well-known shape that's observed. And as you dial the neutrino mass down, it's easier and easier for it to climb out of the potential, and so that suppresses the amount of structure that you see on small scales. And so this is why typically 1 keV is about the scale at which people stop talking about massive dark matter. Now, there is a caveat to this. If I had a way of making dark matter, which is less massive than that, arbitrarily colder than the standard model, okay, then this type of argument doesn't apply. You can imagine trying to build models where that's the case. But nevertheless, because you're trying to detect it in some type of an experiment, that implies a lower bound on the size of the coupling than the standard model, which tends to thermalize it with the standard model at some epoch in the early universe. And so it's typically hard to make it very, very much colder than the standard model. Okay, so 1 keV is a good sort of back of the envelope for when that happens. So let's talk about what other kinds of astrophysical and cosmological constraints that a dark matter candidate beyond the neutrino has to satisfy. So I'm going to come back to the picture that there was at the very beginning of these lectures, where we know actually an enormous amount about the universe from the time that it was a second old. So we can march through each one of these benchmarks, and we had better make sure that the dark matter reproduces the way the universe behaves from that time. So let's look at specific examples. Okay, so starting all the way from the time of the universe as a second old. So late decaying or annihilating dark matter can ionize nuclei and change the predictions of BBN. Okay, so since BBN occurs at 1 MeV or 1 second, this is particularly relevant for any sectors where you would want to decay into the dark matter at temperatures below an MeV. So this is very relevant for gravitino-physics, and that's what's shown in this plot here. If the decay lifetime is small, then you tend to put very strong constraints on the decay of any parent particle into the dark matter plus visible stuff. Okay. It's also extremely relevant for dark matter which is an MeV mass or lighter, because we know from the rate at which the universe expands at temperatures below an MeV that you can't have a lot of additional matter beyond the standard model thermalized sitting around. So that means that if your dark matter is lighter than an MeV, it's probably produced in a non-thermal way. Okay, so sterile neutrinos are one example of a particle that can be produced in a non-thermal way. 2, CMB epochs. So we mentioned earlier that the ringing of these peaks tells you that in addition to baryons, you have a lot of matter sitting around that doesn't have strong interactions. Otherwise, the shape of these peaks would not be reproduced. Okay, and that's fixed basically by the sound speed, which tells you about the baryon to photon ratio, about the baryon density. All these things together, when combined with BBN and the measurements of matter, tell you dark matter should not have strong interactions either with itself at this epoch or with the photons, because if it had, or with the baryon photon plasma, because if it did, it would change the damping of these peaks. So let's look at one particular way in which this very strongly constrains dark matter. So let's take dark matter. So yesterday we had a plot where we showed freeze-in production of newly charged dark matter. Do you remember that? Where the dark matter had a very small coupling to a photon and was produced through rare annihilations of U plus and minus. So let's imagine a similar type of setup. So dark matter, say, has some milli charge, And because it has a milli charge, it could potentially interact with the baryon photon fluid at the CMB epoch. And the reason why this can be particularly constraining is if I look at the interaction cross-section, as a function of the velocity, it behaves essentially like Rutherford scattering. It has a 1 on velocity to the 4th dependence. So that means at the CMB epoch, if the dark matter is relatively massive, we know that it's moving very, very slowly. So that gives a huge enhancement to the scattering cross-section. And so as a result, the effective coupling of the dark matter to the photon, or by extension to the baryon photon fluid, has to be very strongly constrained. And that's what's shown here. So here is this effective coupling to charged particles in the plasma as a function of the dark matter mass, and requiring that the dark matter be decoupled from the fluid at recombination puts a constraint on the effective charge of the dark matter, which is down at the 10 to the minus, depends on the mass here. But you can see that it's around a microcharge. So not even a millicharge. So this constrains the dark matter millicharge. So that's one example where you need to check. Dark matter annihilations in the CMB epoch. So a high rate of dark matter annihilations would inject ionizing and photons into the CMB. So we know that at the CMB epoch, that the electrons recombine with the nuclei. And we know that it doesn't become reionized again until pretty late in the universe, so redshift of a few, when you started to form stars, and the stars produce radiation which can rip those electrons off of the nuclei again. But we also know that that has to happen relatively late. But if dark matter keeps annihilating after the CMB epoch, that is a way in which you can rip electrons off the nuclei. Okay? Either through direct photons or through final state radiation. And they showed that similarly to what can happen if the dark matter has a millicharge, well, the spectrum looks quite different, but you can get a damping in the peaks of the spectrum if you produce any additional radiation. So why is this particularly important for dark matter and hidden sectors? Well, the reason is that as the dark matter becomes lighter, its number density becomes higher, just because you're fixing it to the overall energy density in the universe. And so as a result, you get a very powerful constraint on the amount of ionizing radiation. And there have been a number of updates since this first result almost a decade ago. But the essential physics and actually the constraints haven't changed very much. So if we pick out again this number of a few times 10 to the minus 26 centimeter cubed per second, and then we follow this, because this is what was ruled out by WMAP5, and the constraints have gotten a little bit better recently, but they're sitting right along here. And then you follow where that thermal annihilation cross-section meets the constraint, and it happons right around 10 GeV. So if dark matter is lighter than about 10 GeV, you had better make sure that the annihilation cross-section at the epoch, at temperatures below the CMB, is not still proceeding. So can anybody think of ways around this? So why wouldn't this just kill any type of thermalized dark matter sector? Can anybody think of ways around it? What kinds of dark matter candidates below 10 GeV could be consistent with this bound? What? Anything. What? No, massive dark matter. So let's talk about massive dark matter with mass between a keV and 10 GeV. Sterile neutrinos have the non-thermal production mechanism. So that's one. So, but what about one that was thermalized at some point in the early universe, and it had at some point an annihilation cross-section of 10 to the minus 26 centimeter cubed per second? Asymmetric dark matter, that's one. Another one. Something that annihilates to invisibles, that's another one. It depends on the mass of the invisibles, because now you have to make sure that you don't violate BBN constraints. because we know that there's not a lot of additional radiation at the BBN epoch. Okay, another one.
Something really heavy.
So so let's look at below 10 GeV. So clearly for above 10 GeV, there's a, ordinary S-wave annihilation is still, the number density is low enough that I don't need to think about this bound. P-wave annihilating. Yep, so anything that would have so for example, if the dark matter were scalar instead of a fermion, it tends to be P-wave squared. What? Composite, well that's an example of something that tends to have V-squared suppressed interactions. Okay? And would tend to have so anything where there's a dynamics where, so for example, I could have an annihilation process that would fix, that would reduce the thermal density, and then I could synthesize it into some compound state later on. That's another example. So the point that I want to make is that constraints also very naturally push you into thinking about models which are not S-wave annihilation. Okay? So what I'm saying is that there's another reason that just that what we see observationally would suggest that there should be other kinds of dynamics in the dark matter sector. Okay, so that's another one. So large scale structure. Dark matter halos are not exactly spherical. So the normal picture that we have is that there's a disk. The baryons collapse to a disk because they have photons, which means they can lose energy, but they need to conserve angular momentum. And so the way that you do that is to form a disk. And the dark matter in a typical halo is approximately spherical, but not exactly spherical. Okay, so it tends to look, the gravitational interactions of dark matter means that it tends to retain some of the information about the infall process, and so they tend to look a little bit like squashed beach balls. Okay? But we know that dark matter halos are not exactly spherical, and if the dark matter had strong self-interactions, that would tend to make it more spherical if the interactions were not via a photon that would not allow it to collapse to a disk. So if it had strong interactions, say through a massive mediator, that would tend to randomize the directions of the particles and make the halo more spherical. So you can use that to put a bound on self-interactions. Now everything that I say about dark matter self-interactions, you should take with a big tilde on it. Like a tilde, which is at least 1, maybe 2, or possibly 3 orders of magnitude big. Okay? Because simulations actually are not able at this point in time, even with something as well studied as the Milky Way galaxy, to put very precise constraints on dark matter self-interactions. You go and you talk to a simulator and you ask them, what is the constraint on the dark matter self-interaction cross-section? And they will say, I don't think we really know. It could be 10 centimeters squared per gram, it could be 50, it could be 0.5, we're not really sure. So you see this number floating around actually by a couple of orders of magnitude. Nevertheless, even if you just take that slop, and you say I'm going to put a constraint which is a centimeter squared per gram, which is about 10 to the minus 24 centimeters squared per GeV, okay, and you just say I'm going to take that as a benchmark because it's better than no constraint at all. And then you ask the question, okay, dark matter is scattering through a light force against itself. Okay, what is the constraint on the self-coupling? And so that's what's been derived here. So if I take an interaction cross-section on the order of 10 to the minus 24 centimeters per gram is kind of my tilde back of the envelope constraint, you can see that that puts a constraint on the self-interaction effective coupling constant, which is fairly small. So this alpha x here is an alpha times epsilon squared, just to translate. Okay, so this is effectively a constraint on the dark matter coupling to a massless or a relatively light field. So that's the third one. Fourth one, astrophysical objects. So we know that dark matter can be captured within astrophysical objects. The capture tends to be more effective the more dense the object is. So for example, neutron stars tend to be very effective at trapping dark matter within it. And once you capture dark matter inside one of these objects, it tends to thermalize in the object and then sink to the center. So within the context of limp dark matter, what happens is you achieve equilibrium inside of this object. So the capture and the annihilation becomes balanced against each other. And you can show just by solving the equations that you tend to be driven to where the capture and the annihilation rates are balanced against each other. So as long as the capture and annihilation rate is large enough, this is achieved. And so for WIMP dark matter, the constraints tend to be derived from heating of these objects. Okay? I produce, say, standard model particles, and those standard model particles can heat the inside of these stars. But what if annihilation does not occur? So for example, if there's a particle-antiparticle asymmetry, then only the collection occurs. And you can look at a typical scattering cross-section with a baryon, so 2 times 10 to the minus 45 centimeters squared over the lifetime of the universe. And you take a typical density, which the local density of dark matter here is a little below GeV per centimeter cubed, but let's take 10 to the 3 here to look more towards the galactic center, say. And a typical mass of 100 GeV, and that comes out to be about 10 to the 44. So to normalize that, a solar mass is about 10 to the 57 GeV. So you collect less than 10 to the minus 10 solar mass over a very long period with this kind of scattering cross-section. Okay, so it's not very much mass. On the other hand, it's a scalar dark matter candidate, and it doesn't have Fermi degeneracy pressure, and it picks up the temperature of the ambient neutron star, which is pretty cold, then it tends to sink. And because it tends to sink, even if it's a very small amount of it, it'll self-gravitate. And once it self-gravitates, and it exceeds the Chandrasekhar number, then you can actually form a black hole. And the Chandrasekhar number is a much smaller number. Again, dependent on whatever the mass of the dark matter is. And so as a result, once the number collected exceeds this much smaller number, what you would do is to form a black hole, because because this black hole is still wouldn't tend to evaporate. It's massive enough that it would tend to evaporate, and therefore it would eat the neutron star. So you can see that you actually need very modest cross-sections to be able to make this process happen. Okay. And so that's what's shown here. Dark matter mass, 1 GeV is sitting here. This is an old plot, but this is kind of representative of what direct detection experiments can do. And you can see that there's a region of this parameter space that is excluded by formation of a black hole inside of the neutron star, if the dark matter is asymmetric and scalar. So I'm just using this as an example. Stellar constraints are also important. So stellar constraints, so if you collect dark matter in the center of these stars and it doesn't self-annihilate, it can actually disrupt the main sequence evolution. So that's what's shown here. So along this line is what would normally be called the luminosity versus temperature evolution of the star. So this is the way a star usually evolves. And what they've done here is to take dark matter, which doesn't annihilate, so it collects in the center of the star, and has a typical cross-section that I think is pretty large. I didn't write it down here, but I seem to recall is about 10 to the minus 36 centimeters squared, so pretty large. And a dark matter mass, which is typical of asymmetric dark matter, and then I follow the evolution of the star. And you can see that as I dial up, basically the rate at which I collect the dark matter, that I substantially change the evolution of the star. And that will again allow me to put a constraint on this type of scenario. Probably the most ambitious example of this that I've seen in the literature was the claim that if I can measure the temperature of a neutron star very precisely, I can actually put very strong constraints on any type of dark matter that is able to be captured in the center of a neutron star. So here again, here's the capture rate, so this is the interaction cross-section as a function of the mass. Here's what direct detection experiments can do. And here they have a few projections where if you can measure the temperature of the neutron star to this sensitivity, this is the constraint that you would be able to put on the interaction cross-section of the dark matter. And you can see that they're actually claiming to be able to do substantially better, especially in the low mass window in comparison to any of the existing direct detection experiments. And this is quite literally just kinetic heating. So if dark matter comes in, it's carrying some kinetic energy. If it gets captured, it deposits that kinetic energy on the neutrons in the star. And the claim is that integrated over the lifetime of that star, if I'm able to measure the temperature of the star quite precisely, I can put very strong constraints on dark matter being captured in that neutron star. So I'm gonna actually stop there and take some questions.
First of all, thanks. So, questions or comments or disagreements? Eduardo. I know it's on Eduardo.
Yeah.
Next door.
How simple is it to measure the temperature?
Yeah, that's a $1 million question. How hard is it to measure this temperature? So I'm not an expert on neutron star measurements. I'm told that this number is probably crazy. So you'll notice that if you could get to this type of sensitivity, what it's effectively telling you is you should have just not bothered with the direct detection program at all. Because all this constraint requires is that you capture the dark matter. But I am told that this is crazy. But these curves here, which is a constraint in the 1,000 Kelvin range, is probably doable. So even that is quite remarkable, if you believe this claim.
Yes.
And so how come that much of them so efficiently hit the neutron stars and not other things like the
So typically you'll produce a neutrino. So the question, I should probably repeat it to make sure I heard it correctly. So you asked me if you're heating the star just through the kinetic energy transferred in the capture process, why is it that you're not producing other things like neutrinos?
Yes, and why is it that not other populations are not heating up the star or like neutrinos or things like that, which I can imagine have matter per section?
So this, so for example, let's take Higgsino dark matter, pure Higgsino dark matter. If once it scatters and is captured, so are you asking about the production of neutrinos through an annihilation process, for example?
I'm thinking also of production with neutrino, but you don't have so many neutrinos around.
So in this case, you don't require an annihilation process to do the heating. So in that case, it's the most minimal. So all I have to require is that the dark matter be captured and it have an interaction cross-section. That's all that has to happen. is, so that's why it's an apples-to-apples comparison with the direct detection experiments, is because there's only one process involved. If I'm going to produce neutrinos, it's an additional process, which is an annihilation process, which may or may not be there, depending on my particular model. So I view that as an additional constraint on top of this one. So I guess I could have just gone through more. You should, whenever you have a dark matter candidate, this is what you should start doing is, okay, what is my first constraint? First constraint is going to come from capture. So there's a kinetic heating constraint. It's actually the hardest one to observe, okay? But that one is maybe there in the future. Then the next one is, does it annihilate or not? Okay, if it doesn't annihilate, is it a scalar or a fermion? If it does annihilate, which states does it produce in the final state? So in the case of producing neutrinos, the strongest constraints are not going to come from a neutron star, which tends to be fairly far away. It'll more naturally come from a much closer object like the sun. So in that case, if it annihilates and produces neutrinos, then I should look at the constraints on neutrino production in the sun. So there's kind of like a checklist you should go through, asking, depending on the particular candidate that you're interested in, to look at the various types of constraints. What I wanted to do was to give you here a sampling of the kinds of things that you should go through in your checklist.
So actually, I read something about that the sun can be accelerator, like when the dark matter particles go through the sun, they get accelerated, and then maybe you can possibly detect them on the Earth. So whether it is captured by the sun or it is deflected and accelerated by the sun, depends on what kind of condition.
Yeah, you're referring to this paper by Maxime Pospolov, who I think wrote one of these papers. And as I recall, this was very large cross-sections. So I think the statement is that if the interaction cross-section is large enough, then it can have an interaction near the surface. And so then you can have this process where you get this acceleration. As I recall, that was at cross-sections that was actually very high. It was like up around even above 10 to the minus 30 centimeters squared. We can look again at the plot later on. So yeah, but that is another example of a class of particles, because people have actually also started looking at very large interaction cross-sections. So we've been focused on weakly acting particles because we haven't seen dark matter yet. And that tends to say, okay, dark matter probably has a small interaction with ordinary standard model particles. But it is entertaining to actually think about candidates that, for one reason or another, can evade our usual intuition for looking for dark matter through rare interactions. And that's one case that you're talking about. Yeah, that's right. Yeah, that's right. Yeah. So, yeah, incidentally, that's another direction that's particularly relevant for high mass objects, because the sensitivity in direct detection experiments tends to fall off like 1 on m. And so as the dark matter becomes very heavy, the interaction cross-sections and the constraints in these direct detection experiments can become very weak. And so there you have to start to think a little bit more about very large interaction cross-sections and what's the effect of the overburden and so on and so forth.
The privilege having a microphone. You said that the halo shape that people doing modeling cannot really give hard constraints on self-adapting dark matter. What is the problem? Why can't the modeler not making a good model?
So the basic so you have to realize that that baryons being systematically included in the simulations has been a relatively recent development. is in the last few years where it's really become the norm to do simulations with both dark matter and baryons. And it turns out that the interaction of the substructure with the baryons, both in the bulge and in the disk, is quite important for assessing the substructure. So for example, when a dwarf in the halo passes through the disk, that can actually by itself reduce the central density. It's just the gravitational interaction of that dwarf halo with the subhalo with the disk can reduce the central densities. And so if I have a dark matter self-interaction process that tends to want to make the profile more cuspy in that substructure, and then that passes through the disk and lowers the density again, then you can see how what I might have thought was ruled out before now becomes consistent again. So that tells you basically about the size of the effect, the importance of the baryonic interactions for understanding the substructure of even a halo like the Milky Way. And in those simulations with baryons, people are really just starting to put dark matter self-interactions in. And there's a long debate about how well it is that we actually understand the microphysics to the extent that when you put in dark matter, you're not just tuning, in the baryonic physics, some parameters that allow you to restore the halo to be consistent with the observations. So it's a combination of getting a good enough resolution in the simulations, putting in the baryonic physics, and then adding in dark matter self-interactions in a consistent way in these simulations. And then it's combined, I think, with a cultural thing, which is that I think astronomers, by and large, view dark matter self-interactions as very exotic. And so therefore it's not a high priority item for them. And I don't think it has yet fully penetrated into the culture that self-interactions are fairly generic in theories of dark matter, and that what we should be able to do, a well-controlled theory, that we really understand the constraint, is you put a bound, and then that, as we understand things, that bound decreases monotonically as a function of time. But instead, what you seem to have, we have these oscillations that happen with a period of about a year, where in particular, depending on the group, depending on the simulation. So I think it's not
excluded that to resolve the degeneracy with baryons to come up with a good simulation.
It's not, that degeneracy has not been fully broken yet. That's right. Also because there's a new crisis that appears every few years, it seems, in small-scale structure. In recent years it was the too-big-to-fail problem, which now they say can be fixed with purely baryonic effects, but it also changes the constraint that you can place on the interaction cross-section. And then there's also an additional direction in this plane, which is the velocity. So it depends on the size of the object, the virial velocity of the object that's being simulated. Anyway, that perhaps was, one could discuss this subject for many hours.
Okay, if there's no urgent other counter questions, we should continue discussing over coffee break. Just one short announcement. During the coffee break, at some point, Stefan will take you all somewhere to take a group photo, despite the rain. We wish the sunshine for the group photo, so we have to make
probably it's not raining too strongly. We just do it outside, really, in front of the coffee place. Some of the coffee